And again, lecture 4, page 11. We were just about to discuss something called the probability distribution function, more often the cumulative distribution function, or the CDF. And the notation for this CDF is going to use capital F sub x of little x. And we'll talk about that. All through this, you're going to find I'm going to make a big deal of the fact that this is capital F, not little f. That's because a little bit later, probably in, I don't know, maybe 10 pages or so, we'll be talking about another function that's related to this that is denoted with a small f instead of a capital F. So if you think I'm kind of overdoing the thing about cap versus small, that's why. It's very important to keep these two functions straight. Today we're talking about capital F of x, the cumulative distribution function. So this is going to be our definition, the cumulative distribution function for the random variable x. So in the notation, we're writing the subscript here, sub x, and that's a capital X there, to remind us what the random variable is that we're talking about. So the subscript there tells us the name of the random variable. In this case, the random variable is called x. And then there's going to be a number, a little x here, that is actually a real number. And so the definition right here is capital F sub x of x is the probability that the random variable capital X is less than or equal to the number, whatever the number of little x is of x. Okay? And first of all, notice it is a probability. Notice here it says the probability x less than or equal to x. So therefore, it's going to be true that 0 will always be less than or equal to fx of x, which will be less than or equal to 1, because we already know that that's true for all random variables. Right? So that's the first thing we want to notice about it. Okay? And let's start with an example. In this example, I'm going to kind of go through in excruciating detail because it's the first example we're doing. So notice this is an example where the die takes value 1, 2, 3, 4, 5, 6. So the underlying experiment is the tossing of a die. And the random variable is defined to be taking values 5, 10, 15, 20, 25, 30. In other words, this is the random variable that's taking value 5 times whatever the number is showing on the face of the die. Right? So let's just see what fx of x is for several numbers. So here's my column of some numbers, and I'm just kind of going to fill in some arbitrary numbers here and just fill in, for example, what fx of x would be for those particular numbers. So the first thing is I've arbitrarily, so this is an arbitrary choice here, I've arbitrarily said, let me look at what happens when little x takes the value -1. So the question is then, what's the probability that the random variable capital X takes value less than or equal to -1? Here's my number that we're dealing with, the probability of x being less than or equal to that particular number. So I look up here at all the possible x values and notice that none of them are less than or equal to -1. So the probability of x being less than or equal to -1 then is 0. Okay, so that means when I'm here at -1 on the axis, -1 on the x-axis, the answer is 0. Okay. Then the next question, again, just arbitrarily, I made up an x value, and I said, well, what if x is 4? So the definition, again, capital Fx of x, so the random variable I'm talking about is this random variable we're calling x, and I want to know what's the probability x is less than or equal to the real number, here's my number, 4. And again, I look at all the values taken on by the random variable, and I notice it's never less than or equal to 4. So that's a 0 again. So now when I come over here up to the number 4, I see that the value of the function is still 0. And in fact, if I had put in any other number like, say 2 or 3 or 3.5 for x, then it would be what's the probability x less than or equal to, for example, 3.5, that would have been 0 too. So in other words, it's going to be 0 all the way between negative 1 and 4. And you can try that for yourself. Make any number between negative 1 and 4, and the probability of x being less than or equal to that number would be 0. Okay, so now I know what it is for negative 1 all the way up to 4. And let's move to the next page then. I'm trying to remember. We had 0 all the way up here to 4. We had that the answer was 0. Okay? That's how far we've gone so far. Okay, now the next one says, again, I've repeated the table, of course, just so we don't have to keep looking back. So again, just arbitrarily make up some more x values, like what if x is 5? Well, now it becomes what's the probability x less than or equal to 5? I'll do it up here. Fx of 5 equals the probability x less than or equal to 5. So I look at the table and I see that x is less than or equal to 5 only when x is equal to 5. So I can say it's the same thing as the probability of x being equal to 5, because we notice that x is never less than 5. And the probability that x equals 5, remember we said we back up and find the probability for the underlying experiment. So x is less than or equal to 5 whenever the die takes value 1, and that's of course the number 1/6. So at 5, all of a sudden it jumps from having a value of 0 before that, and then all of a sudden it's sitting up here now at 1/6. Now, I didn't do 4.99999, but we might want to think about that. Suppose x is equal to 4.999, and I want, therefore, fx of 4.999. That's the probability x less than or equal to 4.999. And again, we see in the table that x is never less than or equal to 4.999. So that still would have been a 0. In other words, right up to, until I hit the number 5, the value of the function stays 0. Okay, so now let's take the next kind of arbitrary one here. For fx of 5, we computed that the answer was 1/6. What if we arbitrarily let little x be 7? So now I'm doing, again, kind of up here, a scratch work. Now I'm working out what's fx of 7. By definition, it's the probability that x is less than or equal to 7. But we notice that the only value of x that's less than or equal to 7, so I'm comparing all these values, the only one is 5. That's the only value of x that x actually takes that's less than or equal to 7. So this becomes the same as the probability x equal to 5, and we decided that was 1/6. So when I'm over here at 7, in other words, the answer is still 1/6. And in fact, until I get, well, let me fill that one in. If I had done 9, right, probability x less than or equal to 9, so now I'm looking here. Well, the only number in the set of values less than or equal to 9 is the number 5, so the answer still would have been 1/6. And at 9.999, it would have still been 6. So all the way up, 1/6, all the way up until 10, it keeps that value of 1/6. Right? Now let's try 10. Right? So let me see if I can make some room here. Let me see if I can pick up an eraser. just clearing out some space. Trying to make some room so I can do some more scratch work here. Okay, and now let me pick up the pen again. There's the pen. So now I want to try the probability x less than or equal to 10. So I'm going to do now fx of 10, capital F for the random variable x, evaluated at the number 10. By definition, the probability that the random variable x is less than or equal to 10. And I look at my set of values, and there are two numbers that x could take that are less than or equal to 10. So in other words, this is the same as the probability x equals 5 or 10. Only two numbers that are less than or equal to 10 in this set of x values. But of course that happens when the die takes value 1 or 2. So that's the probability that the die equals 1 or 2. And of course that's 2 of the 6 possible values on the die. And I'm going to go ahead and show that as 2/6 rather than 1/3. It's just going to make my graph look a little cleaner here. So at 10, the value of the function becomes 2 out of 6, or 1/3. Okay, so now we're at 2/6. And notice, if I had done 11.2, it would still be the same, because it would be the probability x less than or equal to 11.2, and the only values less than or equal to 11.2 are also 5 and 10, so I'm still going to be at 2/6. And in fact, if I go all the way over to 14.99999, way over here, right up to right before 15, it's going to still be at 2/6. Okay, now 2 out of 6 if we had plugged in 14.999. Okay, now the minute I get to 15, it's going to take a jump. So fx of 15 is, of course, by definition, probability x less than or equal to 15. So now what values of x are less than or equal to 15? So x can be 5, 10, or 15. X equals 5, 10, or 15. The only values less than or equal to 15 for x. And that happens when the die takes value 1, 2, or 3. And of course that's going to be 3 of the 6 possible outcomes. So it's going to jump up now to 3 out of 6, or 1/2. So at 15, it jumps from, at 14.99999, it had still been 2/6. The minute it hits 15, it jumps up to 3/6. Okay, 3 out of 6. Okay, now how many of these values you really need to kind of go back and look seriously at the definition sort of depends upon you. I'm just going to point out that if we keep going now, every time we hit one of these multiples of 5, like 5, 10, 15, 20, 25, 30, it's going to take a jump. And so just as here it jumped up by 1/6, then it's going to stay the same until I hit 20, and now it's going to jump up here to 4/6. So at 19 it still would have been 3/6, but at 20 it would be 4/6. And then it's going to stay 4/6 until I hit 25, then it's going to jump up here to 5/6. And again, if you doubt that, you can fill in a few more numbers by brute force yourself. When I hit 30, it's going to jump again, and it's going to jump up here to 1, and then it's going to stay 1 forever. Let's maybe just do one more example. Suppose we wanted the probability x less than or equal to 40, just for example. That would be the probability x equals, well, any of these values, 5, 10, 15, 20, 25, 30. 5, 10, dot, 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 going up in multiples of 5, 15, I should have done, let's do 25, comma, 30, any of those values, and of course that's going to be 1, because that's the probability that the die takes any of the values 1, 2, 3, 4, 5, or 6. All right? So if we look at that, we see what's happening is this is an example of what we call a discrete random variable because it only takes, in this case, a countable number of values, 5, 10, 15, 20, 25, 30, and the shape of the CDF, so let's write a little note here that this is an example of a discrete random variable, and the shape of the CDF is staircase. So staircase fx of x. That will always be the case. Discrete random variables will always have a staircase function, and the size of the jump at each of the discrete values assumed by the random variables will be the probability. So in other words, I look at this. If I want the probability x equals 25, the size of the jump there is 1 out of 6. So that's the probability that the random variable takes that value. Okay, so this is the first time we've seen a capital Fx of x function. Let's see if we can go on and make some claims here about the general properties of CDF. Remember, CDF by definition, capital F sub x of little x. By definition, the probability, capital X, the random variable, less than or equal to some number, little x, right? And because it's a probability, we said it'll always be between 0 and 1. If you evaluate it at the extreme left end, which means on the x-axis at negative infinity, it will always start at 0. Remember, I can't go back in this recording here, but basically if you look back at the previous example, we saw that at negative 1, the value of the function was 0, and in fact at any negative number the value would have been 0, so at negative infinity it would have been 0. And in the previous example, by the time we hit 30, the value of the capital F was equal to 1. Well, this just says if you go all the way to the extreme right end of the graph, which means at x equals infinity, the value will still be at 1. It's always between 0 and 1. So extreme left-hand corner is at 0, extreme right-hand corner graphically is at 1. Right? Then the next claim is that it's monotone, non-decreasing. We almost want to say monotone increasing, but sometimes it stays the same, as we noticed in the previous example. Once it hit 30, it stayed 1 forever. So it wasn't decreasing, it also wasn't increasing. So that's why we say monotone, non-decreasing. Right? Okay, then probably the most important property is the way we use the capital F to evaluate probabilities. And the claim is that if I want the probability x is between A and B, and notice that it's extremely important here that we're not including the left-hand endpoint A, but we are including the right-hand endpoint B. Right? So in other words, I'm asking what's the probability of being between A and B, including the B number, but not the A number. So I really want all this probability in between. Include the B, but don't include the A. And the claim is that we should take fx of B and subtract off fx of A. Okay, now I'm going to draw a picture to try and convince you of that, and this is one of the pictures I'll probably be drawing about 20 times throughout the course. So this is the first time now we're going to see it. If I take fx of B, what we're going to do is we're going to say, well, fx of B, by definition, that means the probability of being less than or equal to B for the random variable x. less than or equal to, I'm gonna draw this off the number line itself because it gets too crowded if I put it on the line. But all the probability less than and including B would be everything drawn in that direction. So I'm including the B and moving to the left. Again, theoretically, it should be on the number line. It just gets too crowded if I put it there. Okay? So that's the picture of what we mean by fx of B. It's where the probability is that's less than or equal to B on the number line. All right? Now I want to subtract off fx of A. So let me draw where fx of A would be. Again, in theory, this should be right on the number line, but if I put it there, the picture gets too crowded. So I'm including the A and everything to the left. That's what we mean by where the probability is for fx of A on the number line. It includes the point A itself and everything to the left. Remember, that's the definition. That would be the probability x less than or equal to A. Okay, now I want to subtract that off. So notice I'm starting with everything less than or equal to B, including the B, but then I'm getting rid of everything less than or equal to A. So hopefully you would agree then that what I've included is, I've included the B, I've included all this probability inside here, but notice I'm subtracting off the point A itself. fx of A says include the A when you do your subtraction, so that means we're not including the A in our final answer. So that's how we get the probability of x being between A and B. We don't include the A, but we do include the B. Okay, so that's probably the most important bullet on this page, or the most important property. The next picture is just sort of some sketch of typical CDFs, typical cumulative distribution functions. This one is an example of what a cumulative distribution function looks like if we have a continuous random variable. And a little bit later, we're going to define a random variable to be continuous if its CDF is a continuous function. Remember, continuous means we can draw the graph without lifting our pencil from the paper. So certainly everybody would agree this is a continuous function. Notice that at the extreme left corner, it takes value 0. At the extreme right-hand corner, as I go out to infinity, it takes value 1. And it is monotone, non-decreasing in between. So that's sort of a typical CDF for a continuous random variable. The next sketch is a typical CDF for a discrete random variable. Remember, we said they will always be of a staircase nature if the random variable is discrete. This particular random variable that we're talking about here only takes values 1, 3, and 4, because that's the only place you see jumps in the staircase function. So this is a cumulative distribution function for a discrete random variable that only takes values 1, 3, and 4. All right? And again, notice it started at the extreme left corner at 0, it ends up at the extreme right corner at 1, and it is monotone, non-decreasing. A little bit later we'll point out that whenever you have a discrete random variable's cumulative distribution function, anytime you see the jumps, they will always be open at the bottom, filled in at top. Okay, and that's, again, typical of what we're seeing here. Okay, let's move ahead now. And let's look at our first real-world special case of a random variable. This is a well-known random variable called the uniform random variable. And it happens to have first of all, looking at the graph down here, we can see that it's a continuous function. So this is an example of a continuous random variable, right? Because the CDF is continuous. In particular, it starts out at 0 and it ends up at 1. Again, that's a necessary property. And in this particular case, it's 0 whenever x is less than or equal to some number a on the number line. and then it's 1 whenever x is greater than b over here. So once I get to b, it takes value 1. And that's simply the equation, and then it's linear between 0 and 1. So anytime you have a uniform random variable, it will always have a ramp CDF, ramp function for a CDF, and this particular ramp goes from value 0 to 1. Okay? So we say the random variable is uniformly distributed on the interval from a to b, and the notation we'll use is uniform between a and b. All right? Okay, so that's a nice easy one. By the way, examples are now wiped out. Okay, so I'm backing up to this page, and I just have to record this one over again. So on this page, what we're doing is we're looking at the random variable x that's uniformly distributed between 0 and 2, and we're just going to practice using the definition of capital F to read off some probabilities. So the first question says, what's the probability x less than or equal to 1? So fortunately, that's exactly the definition of capital Fx of 1, right? Definition. Whatever the number is that's the argument of the function, we're finding the probability x less than or equal to that number. So that means I need to read off the amplitude of this function at 1. And this is where you kind of need to use your intuition to say that if I'm going halfway between 0 and 2 in order to get to 1, then I need to go halfway between 0 and 1 to get 1/2. So this height would be 1/2. Similarly, if we wanted the probability x less than or equal to 1/2, because of the less than or equal to sign, it's exactly the definition of capital Fx of 1/2. So I need to go over to 1/2 on the x-axis here and figure out how high this function is. And 1/2 is 1/4 of the way between 0 and 2, so of course this is 1/4. 1/4. Last one, probability x less than or equal to 1/2. Again, because of the less than or equal to, that's the definition. Capital Fx of 1.5. So I read off the value of the function at 1.5, go over to 1.5, which is 3/4 of the way between 0 and 2. So this amplitude has to be 3/4. Okay. And so now we've answered lots of probability questions, taking advantage of the fact that these were all less than or equal to questions. That means I can just read off the amplitude of the capital F graph. So one more example, probability x less than or equal to 27. So that's going to be capital Fx of 27. And we already know that we had hit 1 by the time we reached 2. If I keep going all the way out here to infinity, the value of the graph stays 1. So certainly by the time I get to 27, the value of the graph is still 1. Okay. Let's do another example now. There's a break right here in the examples. All the examples from here up, the sign had exactly matched the definition. The sign of the question we were trying to ask, the probability of x less than or equal to something, exactly matched the definition. Remember our definition, capital F sub x of little x, by definition, is the probability x less than or equal to little x. So now we're going to change that a little bit. The rest of these examples, this one says, what's the probability x greater than 1/2? That does not match the definition. So now we have to turn that around to rephrase it using a less than or equal to. So now we're going to use the idea of complements. If x is not greater than 1/2, then it's less than or equal to 1/2. So we say, remember how complementary events, the probabilities add up to was one of our early corollaries. So in this case, we have the probability x greater than 1/2. We say, well, the complementary event would be the probability that, well, the complementary event would be x less than or equal to 1/2. If x is not greater than 1/2, then it's less than or equal to 1/2. So the probability is going to be 1 minus the probability x less than or equal to 1/2. And this now is phrased correctly for us to read off the capital F function, right? That's the definition, capital Fx of 1/2. And capital Fx of 1/2 we already computed up here to be 1/4. So we have 1 minus 1/4, which is 3/4. And again, it comes from 1 minus 1/4 using corollary 1. Okay, now the next question again is sort of strangely worded. It says, what's the probability x is in the interval from 0 to 1? Right? Well, we could rephrase that as saying that's the probability x is between 0 and 1. Remember, this notation means don't include 0, do include 1. So that really means the probability x is between 0 and 1, strictly greater than 0, less than or equal to 1. And that's one of the rules we had, just, I believe, one page back. Remember, we said we would take fx of b minus fx of a when b is the larger endpoint up here. This is my b number, and this is my a number. I'm trapping x between a and b, where fx of b, this is my b number, the larger endpoint, and I'm subtracting off fx of a, where a is the smaller endpoint. Okay, so x was between a and b, where a is 0 and b is 1. So fx of b minus fx of a, in this case, becomes fx of 1. Well, fx of 1 we computed, and we had 1/2. Right, that was from up here. Right. fx of 0, well, we didn't compute that, but here it is. Fx of 0 takes value 0. You can see that graphically. So I end up with 1/2 minus 0, or 1/2. Okay? So we're using that property that the probability that x is between a and b is fx of b minus fx of a. Okay, now this next one's a little bit subtle. This next one says, what's the probability x equals 1? All right, well, it's kind of a trick question. For continuous random variables, the probability of x taking any discrete value is 0. Okay, for any continuous random variable, the probability that x takes a specific value is 0. And we'll see that a little bit more rigorously in a minute. And the reason that's kind of important to note now is because now we're going to look at a slightly different problem. We're going to take this problem and modify it. Notice up here in this line, we are saying what's the probability that x is between 0 and 1? Don't include the 0, but do include the 1. Now we're saying, well, don't include either of the points. Okay? So I want the probability x is between 0 and 1. So in other words, now we're doing, let me write it over here, the probability 0 less than x, strictly less than 1. I'm not including either endpoint. But we noticed that the probability of x equaling 1 exactly was 0 anyway. So it doesn't really matter whether you include this endpoint or not. The probability of x taking the value 1 exactly is 0. So whether I include that endpoint or not doesn't make any difference. In other words, this answer up here will be exactly the same as the answer down here. Because again, the probability of x exactly taking the value 1 was 0. So again, what we get is 1/2, the same answer we had up above. Okay, let's try and move on here. Okay, so let's make some conclusions now about discrete and continuous random variables. So discrete random variables are random variables that take a countable number of values, like 1, 2, 3, and so on, and they always have staircase cumulative distribution functions. And the probability of the random variable taking any specific value is given by the size of the jump in the cumulative distribution function at that point. Okay, now I can't back up to a previous page because I'm recording this, but I'll show you some examples of that when we're physically present next time. Continuous random variables take on a continuum of values, not a countable number of values, and they have continuous CDFs, but it turns out that this rule will still apply. The probability of the random variable taking any specific value is still the size of the jump in the CDF at that value. And notice there's some parenthetic remarks. Probability of continuous random variable taking any specific value is 0, but that's the same as the size of the jump, because remember, there aren't any jumps. So if there isn't any jump, it's like saying the size of the jump is 0. And this remark is just that uniform random variables are examples of continuous random variables. Okay. I'm having trouble picking up the pen on page 17 here. Let me try again. Okay, there we go. So the extreme left end over here, the CDF takes value 0. The extreme right end, it takes value 1. And so what we're saying now is this is sort of an example of a continuous function moving from 0 to 1. And in this particular case, the random variable is continuous. It's actually continuous everywhere, but it takes on meaty values, say the interesting values, between A and B. In other words, that's where it goes from 0 to 1. And if we ask ourselves what's the probability x takes value x naught, this value right here, notice there is no jump. It's a continuous function there, so the probability of x taking that value is 0. All right? As opposed to if we look at an example of a discrete random variable, and say my fx of x, let's suppose it looks like this. Just making up an example here. So at 0, it takes jump and goes up to 1/2, let's say. And then over here at 1, so it stays like that. At 1, it jumps up to the value 1. And suppose that's my example of a discrete random variable. Now for this random variable, if we ask ourselves what's the probability that x equals 1, it's going to be the size of this jump. And the size of this jump is 1/2. So that's the probability that x takes value 1. The size of the jump in the cumulative distribution function. Okay, I can pause for just a minute because my dog is going bonkers here. Okay, so hopefully we're back recording now. So we were just saying that we were doing the example here to show that whenever we have a continuous random variable, the size of the jump is the probability, and similarly for a discrete random variable, the size of the jump is the probability. The difference is that up here, when we're talking about the generic one, there is no jump, so the probability of x taking any specific value turned out to be 0. Okay. Okay. Okay, so going on, let's look at a specific example of a continuous random variable. So for this particular example, suppose we have an experiment and suppose we're testing diodes. testing diodes, and we're going to start the test at t equals 0. And suppose we define a random variable t, which is the time to failure. How long does it take before this particular diode that we're testing fails? Right? So that's my random variable. And suppose there's a company, and the company has kept some statistics, and they know that the probability that the random variable fails before time little t is given by this equation, 1 minus e to the minus mu t. And mu, we say, is a parameter of the distribution. So in other words, to know the exact failure probabilities, we're going to have a number for that. Somebody will give us a number for mu, the parameter. But that's basically my equation for the probability that the diode fails before time little t. So by definition, that's capital Ft of t. Okay, now suppose we're asked to compute the probability that the diode fails between 2 points in time, t equals a and t equals b. Okay, now the little footnote at the bottom here is really important. The little footnote says, don't worry about the endpoints because this particular capital F, that's a continuous function. If it's a continuous random variable, we don't have to worry about the endpoints. Remember, every endpoint occurs with probability 0, so it doesn't matter whether you include them or not. So in other words, if I want to know the probability that it fails between time A and B, that would be Ft of B minus Ft of A. Remember our rule, f of the larger number of the endpoint minus f of the smaller. Another way of saying it, if I want the probability it fails between time A and B, I take the probability that it fails before time B, subtract off the probability it fails before time A. So number-wise, I'm doing this. Here's my A point. Pick up another pen if I can find one over here. There we go. Okay, so on the number line, I'm doing this. Here's the number A, here's the number B. I want to know the probability it fails somewhere in here. So again, I take f of the larger number, that's capital F of B, and I subtract off f of the smaller number, that's capital F of A. Notice in this case, the name of the random variable is capital T, so we say capital F sub T of B. We subtract off capital F sub T of A, and what we get is the probability that fails between time A and B. Okay, so same old rule. And we have equations. Again, whoever is the quality engineer for the company, quality control engineer, he has an equation. He says, well, in general, it's going to be capital F evaluated at B. So I take this equation. That's 1 minus e to the minus mu b. And then I subtract off capital F of A. So again, this is capital Ft of B. I subtract off capital Ft of A, just using the equations up here. Right? And then we notice the 1's cancel, and because of the minus signs here, it becomes e to the minus mu A. That one comes out in front, and we're subtracting off, again, because of the minus sign here, e to the minus mu b. Okay, so that's my answer for the probability of failure between time A and B. Now, that's not a very satisfying example. You don't get much of a feel for it unless we fill in. Okay, let me try this again now. So basically, I was mentioning on the previous page that you don't have much of a feel for what this graph looks like unless you pick a parameter mu and graph it. So the equation of the graph here, this is the equation for 1 minus e to the minus mu t, but mu is 2, so that's what I'm graphing there. And of course, the t parameters go along the line here. So for mu equals 2, assume that t is measured in months, notice no units were given before. So now I'm saying let's assume that the time is given in months, and this is find the probability that the diode failure occurs between 1 and 2 months. So in that case, what we're asking is failure between 1 and 2 months. It's like on the number line, I want f of 2 would be all the probability over there, ft of 2. And I want to be between 2 and 1 month. And then ft of 1 would be over here, all this probability, that's capital Ft of 1. And if you take ft of 2, subtract off ft of 1, what you get is the probability of being between 1 and 2. So graphically, here's my ft of 2 number, and I'd have to plug into the equation, and I'm going to do that down here. The probability of failure between 1 and 2 months is ft of 2 take away ft of 1. Always capital F of the larger value minus capital F of the smaller. Here now I'm plugging in the equation for ft of 2, 1 minus e to the minus 2 times 2. This is the parameter mu, and here's my specific t value. And then I subtract off ft of 1, well, here's the parameter mu, and here's the value t equal to 1. And when we subtract those off, remember the 1's cancel, and you get e to the minus 2 times 1, subtract off e to the minus 2 times 2. That turns out to be 0.117. Alright? So that's the probability then that the part fails between 1 and 2 months. Okay. Okay, so again, continuing on a little bit with CDF properties and classification, we've already said that the probability x taking any particular value is the size of the jump in fx of x at x equals a, the point of interest. And sometimes that might be 0, particularly if it's a continuous random variable. We've already mentioned in class 2 that fx of x, the graph, is always right continuous. That means if there are any holes, not all CDFs have holes, but if there are holes, the holes are going to be filled in on the top and open on the bottom. So here's sort of your typical sketch of one that is that has a jump at a particular point, and the hole is open at the bottom, filled in at the top. And some claims, again, about classification. The CDF is continuous if the random variable is continuous. The CDF is staircase if it's a discrete random variable, and anything other than that would be a mixed type random variable. This is an example of a mixed random variable. So this is a CDF for a mixed random variable. Why is it mixed? Well, it certainly isn't staircase in general. Staircase functions are flat everywhere except for wherever they have jumps. So this is not a staircase function, and it's not a continuous function because it's got a gap right there at whatever that particular value is. So therefore it's neither continuous nor staircase, so therefore the random variable is a mixed random variable. Okay, then the last bullet here is fx of x is monotone, non-decreasing. Formal definition of that is whenever the x1 value is strictly less than the x2 value, then the fx CDF evaluated at x1 is less than or equal to. It can never be bigger than fx at x2. So it's basically saying as I move from left to right, x1 is less than x2, so I'm moving from a smaller to a larger, from a lesser number to a larger number on the number line, right, from left to right. Then I can't possibly be decreasing in the amplitude. Okay, that's all that's saying. Okay, CDF review, we've already done quite a few points. Let me fill in a couple more here. So point number 1 would be 0 less than or equal to fx of x less than or equal to 1, because again it is a probability. Another point would be the definition, not definition, but the really important rule about finding the probability x being between A and B, where we're including the B but not the A, is fx of B minus fx of A. And then a little note here, now we can say including or not including endpoints doesn't matter for continuous random variables. So you can be sloppy with these signs, right? Whether they say strictly less than or whether they say less than or equal to. You can get away with being sloppy on the signs if it's a continuous random variable. If it's a discrete random variable, you have to be really careful with the signs. Okay, I think that's probably the only ones that we, I guess one other thing is third point in the way of review, the probability x equals A is the size of the jump in fx of x at x equals A. Okay, so the size of the jump at the particular point A is the probability that x takes on the particular random variable. Remember, continuous. Okay, so now we're going to introduce a new function called the probability density function. I mentioned at the beginning of class tonight that I had to be really, really careful about whether I included or did not include I had to be really, really important about whether I really careful about whether I used capital F or little f when I was talking about the CDF. And for the CDF, we said we had to use capital F. That's because now we're introducing this thing called the probability density function, which is going to be little f sub x of x. So whenever I write this, especially for the first half of the course or so, I will always try to say whether I mean capital F or little f as I read what I'm writing, because again, if you get these messed up, you're in trouble. Okay, so suppose we start with the idea of a continuous random variable, capital X, and we recall that the definition of capital Fx of x is just the probability that the random variable, capital X, is less than or equal to the number, little x, and that's called the cumulative distribution function. So now we're ready to define the little f function, that is the probability density function. So little fx of x is by definition the derivative of the capital F. And when we take the derivative of the capital F, we get the probability density function for the random variable x. So because of the fundamental theorem of calculus, we know that if little f is the derivative of capital F, then capital F is the integral of little f. And when we write this integral, we often use dummy variables. So I'm writing little fx of t and integrating dt. If I integrate from minus infinity up to little x, then I get fx of x. Right? So little x is the upper limit on the integral here. It's the number that is the upper integral. So if I want to compute the probability that x is between A and B, And we know that means the probability x is less than or equal to b, because again, I'm trying to be careful here with the endpoints, even though we don't really have to for the continuous random variables, but I'm just going to be careful for the sake of definition. So it's the probability, I'm asking what's the probability x is between a and b, and I want to include the b. So I take all the probability x less than or equal to b, again, all this probability over here, all the way over, that's fx of b. And then I subtract off all the probability left of and including a, capital Fx of a, and then I get the probability between a and b, where I'm including the b and not including the a, right? So we already had decided that, so that's fx of b minus fx of a, right? We decided that already. But now we're saying, well, how would you get it in terms of the little f? So I should integrate the little f up to b, because remember we said if you want fx evaluated at x, you should integrate up to x. I want fx evaluated at b, so I should integrate the little f up to b. For fx of a, I should integrate little f up to the number a. Just integrating little f up to a. And from calculus, you know that if you integrate all the way up to b, and then subtract off the integral all the way up to a, what you get is the integral between a and b. So this is really important now. This tells us that if I'm using the little f function, I need to integrate little f between a and b. Okay? Remember, we're talking about continuous random variables, so it doesn't really matter if you include the endpoints or not. This could just as well have been strictly less than b here if we wanted it to. Okay, so see if we can go on. Okay, so on this page we're basically summarizing some of the properties that we just mentioned, or some properties, excuse me, of the probability density function. So this first one is just reminding us that if we want to get the probability of x being between a and b, we integrate from a to b little fx of x. Right, that's the integral from a to b little fx of x dx, or t dt if you prefer, either way is fine. Couple of notes about probability density functions. One is they better always be non-negative. And here's a bad example. Here's a bad PDF example. So you don't particularly want to put this in your notes, but suppose I had a PDF that did this. Suppose this happened at 1 and this happened at 2. What happens is if I did the integral from 1 to 2 of this bad fx of x up here, dx, it would be negative, right, if I'm using this function. So that can't happen. We know we can never have negative probabilities, right? That would be the area under the curve between 1 and 2 would be negative. That can't happen. Therefore, fx of x can never be negative. On this example, I was showing one that went negative between 1 and 2. It gives me a probability of x falling between 1 and 2 that's a negative number. Therefore, that can't happen. Okay, now this next point is more subtle, and we're only going to use this one point, and it's kind of a theoretical thing. But what it says is if you want the probability of x being between 2 points, specifically like a specific x and an x plus dx, so here's my specific x value, here's my x plus dx, so that the width from here to here is dx. So if I want the probability of x being between those two numerical values, it would be, well, it would be the area under the curve, which is the blue area. But remember, in calculus, we often approximate that by taking the height of the rectangle. height of the rectangle here is fx of, in fact, I wish I'd called that x naught, and this is x naught plus dx, right? So the probability that capital X is between x naught and x naught plus dx. Well, this point right here, the height of the rectangle, that's fx of x naught. The width of the rectangle is this dx, so my approximation for the area under the curve is the area of the rectangle, fx of x naught times dx. That's the shaded, the dark shaded area here. Notice it's not quite the same as the area under the curve, that's why there's an approximate sign here. So we're approximating the area under the curve by the rectangle, fx of x naught times dx, alright? And the moral of the story here is that probability is not found by just taking the height of the function. It's the height times some little chunk dx, alright? And then the last little bullet is, of course, if you integrate the entire density function, you better get 1 because that's the total amount of probability. Okay. Okay, a couple of facts about cumulative distribution functions. Remember, that's capital Fx of little x. And the probability density function, that's little f sub x of little x, right? So, a couple of facts about that. One is either one of those makes a complete description of the random variable. In other words, if you know little fx of x, you can answer any probability question. Similarly, if you know capital Fx of x, you can answer any probability question. And knowing one, you can always find the other, right? If we know capital F, we differentiate to get little f. If we know little f, we integrate to get capital F. So we would say then that they are information equivalent. Knowing one enables me to answer any question that I can answer using the other. They have the same amount of information in them. And knowing either one of them enables me to answer any probability question about the random variable. So in other words, they kind of tell a complete story about the random variable. Either one of them by itself would do that. Okay, let's take an example now, kind of relating little f to capital F. We've already talked about what it means for x to be uniform between A and B. So in this case, I'm going to say uniform between A and B, where the A value is 2 and the B is 5. And we knew that the capital F started at 0, ended up at 1, and increased linearly then from the 0 value to the 1 value on the domain between 2 and 5. Okay, so that's the capital F for this particular random variable, uniformly distributed between 2 and 5. So now what we want to do is we want to find the little f, right? We said they were information equivalent, so we ought to be able to use capital F to find little f. So I look at this graph, and the first thing I do is I say, well, let me look at the function right here to the left of 2. And let me think about what the slope is, right? The slope of any constant, or excuse me, the derivative of any constant, remember, is always 0. So the function is constant to the left of 2. So the derivative is going to be 0 to the left of 2. So here I have value 0 to the left of 2 when I'm taking the derivative of capital F. So going from here to here, I'm doing ddx. Now, over here to the right of the number 5, the value of capital F is constant again. So capital F is constant to the right of 5. Therefore, the derivative is 0 to the right of 5. So again, I'm back here at value 0 in little f, because again, the derivative of any constant is 0. Okay, now the only place left where anything interesting can happen is between 2 and 5, and we know the derivative of a line is the same as the slope. Remember, in general, the derivative is the slope of a tangent drawn to the curve. If it's a linear function, then the derivative is just the slope of the line. So the slope of this line, notice you go up 1 and you go over 3, going from the 2 value, say, to the 5 value, right? You rise 1 and you run 3. So rise over run is 1/3. So the derivative on the interval from 2 to 5 then is 1/3. So there's my derivative of capital F. It has value 1/3 between 2 and 5. Okay, so our claim is then that's the probability density function of a random variable that's uniformly distributed between 2 and 5. Okay, you should always check when you do a calculation like this to make sure that the area is 1. And notice that this is simply a rectangle here. And the width of the rectangle from here to here is 3. The height of the rectangle is 1/3. So the area of the rectangle is 1. Okay? Okay, now let's just point out that when we originally introduced the definition of a uniform random variable, we said, well, it's uniform if it has this ramp shape CDF. But that's not really what the name comes from. It's really much more interesting to look at the PDF. Uniform means the random variable has the same amount of probability over any little chunk. So if I took a little chunk of width dx, and if I looked at that area under the curve there, and if I took another little chunk over here of the same dx and found the area under the curve there, this area of width dx would be the same as this area of width dx. So every little chunk dx has the same amount of probability associated with it. That's why it has the name uniform. It doesn't really have much to do with the ramp function up here, right? So we use the uniform random variable whenever we have something that's equally likely to do, well, to take on certain probabilities over regions of equal width, right? So that's what we're talking about. Okay, so let's do an example. First of all, let me clear up this. I don't want to clear up the whole slide, but let me at least clear up this a little bit so I can change the question slightly here. Here we go. Okay, so now I want to address this question at the bottom, the probability that x is between 1 and 3 using this graph up here. First thing I can do is I can say, well, x is never less than 2, right? Because all the probability lives between 2 and 5. So I'm going to change the question to the probability 2 less than x less than 3. Because again, x is never less than 2. I can see there is no probability to the left of 2. Now I say, well, how much area is there between 2 and 3? So I move over to 3 here. Now the width of this rectangle from here to here is 1. The height of the rectangle is 1/3. So 1 times 1/3, 1 times 1/3 equals 1/3. Again, I took the area under the curve between 2 and 3. The width of the rectangle times the height of the rectangle. All right? So the answer is 1/3. Okay, let's move ahead from there. Okay, now we want to look at what happens when we do probability density functions for discrete random variables. So far, the one we looked at, the uniform one, was an example of a continuous random So this time we have one that's discrete now. In particular, let's look at the fx of x that has a staircase example. Again, we know that if I take capital F and do the derivative, I should get little f. So I would like to differentiate this capital F function, and notice that capital F is constant between 0 and 1, not including the 1, but it's constant here between 0 and 1. So to the left of 1, I'll put a little open circle here, to the left of the 1, I have a constant capital F over here. When I take the derivative of that constant, I get 0. So I know the function is going to be 0 up until I hit 1. Okay, between 1 and 2, not including the 1 and not including the 2, but between 1 and 2, the function up here is also constant. The derivative of that constant is 0, so again I get 0. So 0 here, 0 here. At 2, that's a different story. Okay, now if I go to the right of 2, so now I'm looking over here to the right of the 2, again the value of the function is constant, and the derivative of a constant is 0, so again I'm at 0 for the little f function. Okay, now we haven't said what happens at 1, okay? So now I need the derivative. Remember, the definition of derivative is the derivative of a tangent, the slope of the tangent drawn to the curve. Well, this curve is jumping up here, right? And the derivative then, it's like, if you think of it as rise over run, you're rising 1/2 and you're running 0, right? There's no horizontal movement in this vertical line here. So you're rising 1/2, you're running 0. 1/2 divided by 0 is infinity, right? Another way of saying it, the slope of the tangent line drawn to this curve, well, it's a vertical line here. So the slope of the tangent line is infinity. So at 1, I need the value of the function to be infinity. That's a delta function, right? It has amplitude infinity. Similarly, at 2, notice the size of the jump here is 1/2. The size of this jump is 1/2. Again, 1/2 divided by 0. Rise over run would be infinity, or the slope of the tangent drawn to this curve. It's an infinite slope, so that means we need infinite amplitude at 2. Okay, now the way we capture the height of the jump, because somehow we want to quantify the size of the jump with these delta functions, and we do that by saying the area of these deltas is the size of the jump. So the size of this jump was 1/2, so therefore this is a delta with area 1/2. The second one also, it's going to be a delta because it's infinite height, but the area under the curve has to be 1/2, the size of the jump. Okay, so in other words, whenever you have a staircase, a staircase capital F, when you take the derivative, you will always get a sum of delta functions, just a bunch of delta functions for the little fx of x. Okay? And the area of each delta function in the PDF will be the size of the corresponding jump in the capital F function. Okay, so I think we've talked an hour and 15 minutes now, so I'm going to cut this off. Move to the end of the presentation to stop it, I think.